And welcome everyone to today's session of Seminario Flotante. Our speaker today is Mariana Vicaria from University of California at Berkeley, and she will be talking about elimination of imaginaries in order abelian groups with bounded regular rank. So thank you, Mariana, for accepting the invitation, and the screen is all yours.
Okay, thank you very much. Maybe I will start by saying that I'm very happy to talk in this seminar. So thanks for the invitation. I'm always glad to talk for Bogota. And actually, I have chosen like the topic among the stuff that I have done that I thought will be more popular among some of you. So I hope like John shows up eventually at some point. So yeah, I'm going to talk about elimination of imaginaries in order Billing groups with bounded regular rank. That maybe for those that are familiar with the topic, you might prefer like the terms with finite spines. But I prefer this terminology because it's more related to the classical language or terminology that was introduced in the 60s, and it preserves like the nature of the convex definable subgroups. So I hope you enjoy. Also, I prepare like the talk for general audience, like not only mole theorists. So if at some point I miss something, please just stop me and then I will introduce the terminology that I'm using. So, okay, what is elimination of imaginaries? Let's start by what is an imaginary and what is the well-known Sherlock's expansion. So you're going to be given a first order theory and its monster model. And what is the business here? Well, you're going to have a definable set in your monster model and an equivalence relation over that definable set, D, let's say. And if you look at the equivalence class of some element down to this equivalence relation, well, we're going to call that equivalence class to be just the imaginary element. And the first appearance of imaginary elements was in Shella, like classification theory, but the language that we use nowadays was introduced by Mackay. So what he proposed in order to deal with these imaginary elements was consider your monster structure, and we're going to increase the language. So what we're going to do is to add a sort for each possible equivalence relation that we might have. And a map that is essentially sending each element to its respective class. And this is well known to be the imaginary expansion of M. And usually we refer to the sorts that we added to be the imaginary sorts, while we refer to the original ones as the home sorts. And sometimes I will also refer to the elements in A as real elements instead. So what is relevant about this is always that you have a definable set or like actually a formula that is going to induce a natural equivalence relation over your monster model by essentially the set of parameters. So the equivalence relation is going to hold if and only if it essentially defines the same phi instance. So essentially for every element phi of x, y will hold if and only if phi of x, c will hold. And canonically for each definable set, if you put a parameter b here, you might consider the class b quotient this equivalence class, and we refer to that element as the code of x. And usually we denote it in this way. So another way to think about the code, and is the one that is more useful when you're working with this stuff, is thinking in terms of automorphism. That is essentially for any possible automorphism that you have for the monster model, the set or its equivalent, like having the set to be invariant over the action of the automorphisms, is the same group of automorphism that fixes this element and backwards as well. So what is elimination of imaginaries? Always that you're going to have a first order theory and a monster model M. I'm going to say that the theory has uniformly elimination of imaginaries if for any possible definable equivalence relation that you give me, I can give you back a definable function such that for any two elements, they two are going to be related even only if the value of the function is the same. So essentially, you might look or find a function such that the fibers of that functions are precisely the classes of your equivalence relation. And the nature of this, or the reason for which I like more this definition, is because it preserves like the idea behind elimination of imaginaries, that is somehow you have a definable way to name each of the equivalence classes. And one can think about elimination of imaginaries as well as, well, you have this class of definable sets and you want to sort of preserve or increase the language such that they're closed under quotients or definable quotients. There is a slightly weaker notion and concise with these ones whenever you have at least two constants in the language. That is the canonical elimination of imaginaries. So we said that it will have elimination of imaginaries if for any possible imaginary element that you have, you can find a real tuple such that the imaginary is interdefinable with the real tuple. And examples of theories that have elimination of imaginaries, well, in fact, this is very similar to the canonical or standard quantifier elimination, and it's a question that is related to the language. And the reason is, well, if you consider the Monster model M and you go to MEQ, well, MEQ has always elimination of imaginaries because, in fact, you brutally added everything that you needed in order to quotient or name everything definably by quotients. So asking in general about elimination of imaginaries is always a question that you would like to somehow refer to a language, in the sense that you don't want to brutally add everything, but you want to add only or to consider a language that is still reasonable where you still have elimination of imaginaries, as you do for quantifier elimination. So for quantifier elimination, the version should be like you could moralize, you add predicates for each possible definable set. That is not interesting. You would like to keep like a reasonable language in which you have quantifier elimination. So the canonical examples or algebraic examples are like, say, the theory of algebraically closed fields in the language of fields, differentially closed fields of characteristic 0, when you add these ones also like with the derivation ACFA, which is just the model companion with of the theory of fields with a generic automorphism. So you will have elimination of imaginaries over this one if you add this one. PA, if you consider the language of rings with the order, real closed fields also with the language of fields with an order, and so on. Okay. Okay, and among all these very big notions, there is a slightly weaker notion, that is those that have weak elimination of imaginaries, that are essentially those theories that have elimination of imaginaries for pretty much all the equivalence relations, except for those that code the act of permutation of over finite sets. So a theory is going to have, or we say that has weak elimination of imaginaries if for every element you can find, or imaginary element, you can find a tuple in the home sort such that E is going to be definable over A, and A is not going to be definable over E, but is instead going to be algebraic. And we say that a theory is going to have, or to code finite sets, if for every possible model, if you consider a finite set of tuples in M, then you can find a tuple that is interdefinable with the code of S in M. And this is the fact that I was referring to. So whenever you have complete multi-sorter theory, first order theory, if you have weak elimination of imaginaries and you code finite sets, then the theory has elimination of imaginaries. And well, there are many examples, let's say, across everything about weak elimination of imaginaries with node AE, or full elimination of imaginaries, that is the theory of infinite sets. Or more importantly, for our case, it will be the theory of vector spaces over FP with dimension at least 2, which is fairly easy, and I will go a bit over the details over this one because this plays a fundamental role also on the optimal on the optimality of our statement. So what happens in FP and why you cannot code a finite set? So let's say that you have a vector space of dimension at least 2. So you might pick up two linearly independent sets, U and V. And what is our goal? Well, we want to show that there is no tuple in the vector space, such that for every possible automorphism that fixes the tuple, it will make the set invariant and vice versa. So the first part is, okay, let's assume that you have some tuple that is actually definable over the code of this set. So that means that whenever this set is invariant over the action, it will fix also this element D. And then each of the coordinates of this dA, I'm going to argue that it will belong to the span of the sum of the two elements u and v. So the trick is canonical. Just consider the automorphism that permutes u by v. This is going to make this set to be invariant. But by hypothesis is also fixing all the possible coordinates of the tuple D. So in particular, this element D must stay fixed under this action. So it is going to belong to the span of U plus W, U plus B. But the point is, well, now what happens with the other way around? In fact, any of these two elements, U and V, by the linear independence, do not belong to the span of P of the sum. So you might find an automorphism again by just basic linear algebra that fixes the sum, but does not fix each of them. So it's going to move U and it's going to move V. However, this automorphism will fix each of these tuples, thereby it will fix also D. So in fact, what we have found is that we might found like an automorphism that is going to fix the tuple D, but is not going to make the set invariant. So essentially, there is no way to find a code for this finite set over the vector space. And well, the argument for n of them will work like for n linearly independent and so on. So there is no chance that we can code finite sets over FP vector spaces of dimension at least 2. And the next part is, okay, what I want to do is some sort of try to understand how to eliminate imaginaries in order abelian groups. And I was mainly motivated by eliminating imaginaries over valued fields. And I was tremendously surprised by having this question to be open, in fact. And the reason is somehow we do know a lot about order abelian groups, or fairly enough, and they have been studied since the 60s, more or less. But no one, I guess, had tried like to eliminate imaginaries so far, as my knowledge brings. And I would like to sort of shortly or briefly make like a history path across this. So in fact, what do we know? Like since the 60s, Robinson and Sacon, and as it is normal, Robinson initiated the area by identifying or isolating the notions of regularity and characterizing all the possible completions of the theory of regular order abelian groups. So what is that? Let's say that you have an order abelian group. Then I'm going to say that an element in that order abelian group is going to be indivisible if you can find an element in the group such that n times beta is going to be equal to gamma. So, and I'm going to say that an order abelian group is n regular if for any interval with at least n elements, you can find an element that is indivisible inside that interval. And more generally, we're going to say that an order abelian group is going to be regular if it is irregular for all n. So what is the theorem that they introduce? Sort of the main folklore or the main distinction that one has between order abelian groups is, well, always that you have an order abelian group, you will have a topology induced over that one that is induced by the order topology. And it is going to be discrete if and only if there is a minimal positive element that we're going to denote as 1. And what they proved is that the possible completion of the theory of regular groups are essentially of two kinds. It is either the theory of discrete regular groups, which is just Pressburg arithmetic, or it is going to be a dense regular group. And then everything that you need to establish, like to make it complete, is to identify which is the quotient or the size of the quotients of gamma modulo p gamma. And they did much more work, let's say, towards this direction. They actually showed that any regular order abelian group is always the elementary equivalent to some Archimedean group. And one can think about these ones as those that are rank 1 in the sense that they do not have definable convex groups. And the canonical examples are those that are definably complete, which are order divisible abelian groups and the theory of Pressburg arithmetic. There is a further step that was taken in 2003 by Beligradec, who introduced the notion of polyregularity. So if you have an Ordovilian group, we're going to say that it's polyregular of rank precisely n if you can find a sequence of convex definable subgroups, let's say of length n, delta 0, delta 1, and delta n, such that each of the quotients is going to be a regular group, and you require that for those that are smaller than n, the quotient is not divisible. So maybe, well, the canonical example of this one is just the product of the integers with itself with the lexicographical order, or finite products of regular groups with the lexicographical order. And then he did much, much better. So he characterized, in fact, that these are the only ways to obtain polyregular groups. So if you have a pure Ordovilian group, the following statements are equivalent. So you're going to have that the group is polyregular of rank less or equal than n, or is equivalent to having at most n proper definable convex groups, all of them definable over the empty set. And it's the same as saying that gamma is elementary equivalent to a subgroup of the group R to the n with the lexicographical order. And there is a bigger class that maybe is the one that I am going to refer to, which is those that have bounded regular rank. That actually, I didn't know how to attribute this part, because pretty much all the model theory so far that we knew about quantifier elimination relative to the orders and so on, that is present in Smith habilitation thesis. But then there are like further refinements that were obtained later. And actually, one quantifier elimination relative to the auxiliary sorts was also like reobtained by Imi and Kluckers. So this, let's say, like the big theory was developed by Schmidt, and then refinements have been obtained like by further other people. In this case, I'm going to refer to Fabre, who isolated the notion of bounded regular rank. So if you have an Ordovilian group gamma, I'm going to say that it has n regular rank equal to m if you can find a sequence of convex subgroups such that the same happen. So essentially, you're going to require the quotient to be n regular, and for each of them, they're not going to be n divisible. And if this happens, then I'm going to denote as Rg sub n gamma, just the set of these convex subgroups that we need, which are called to be like the n regular jumps. And some way to think about it is like how many steps you need to quotient by such that you will obtain at some point this regularity. And in general, if you have that for all possible n, you have finite rank, then I'm going to denote as Rg gamma, just the union of all these convex groups that you might need, which are going to be countably many, in fact. And for it, in fact, later characterize completely this class. So if you have an Ordovilian group, the following are equivalent. So it is going to be true that for each of the primes, you have finite pure regular rank. For each natural number, you have regular rank. There is a cardinal kappa such that for any possible other Ordovilian group that is elementary equivalent to gamma, you will have that the size of the convex groups, or the cardinality of how many convex groups you have is going to be bounded by kappa. For any other Ordovilian group that is elementary equivalent to gamma, you will have that any definable convex group of H is going to be definable without parameters. For any possible elementary equivalent group to gamma, we're going to have that H has at most kappa, or actually countably many definable convex subgroups. So this is a nice class, and the reason is you don't have too many convex definable subgroups. They're controlled, they're just countably many. And in fact, all of them are going to be those that appear at some point in these regularity chains. So whenever you consider like this mega union, that has all the possible convex groups that you might be interested at, and all of them are going to be definable without parameters. And this is sort of related with the standard terminology that is around nowadays with the order Boolean groups, which are those that have finite spines. So for those who are familiar with that terminology, I will say that for array also proves that an order Boolean group is going to have bounded regular rank if and only if it has finite spines. And this is probably like the key point, and you will realize that pretty much everything about eliminating imaginaries in this class is just reduced to having a nice quantifier elimination. So it is just that it is sometimes like a bit tricky on the terminology, but I will try to introduce that. So the canonical Pressburger language is you just add two constants, 0 and 1, extending the language of order Boolean groups and equivalence relations. That how do we interpret them? Well, we of course like the part that is for a group extending just the language of order Boolean groups, that is going to be like just the obvious interpretation. The one is going to be a distinguished element. So if gamma is discrete, I'm just going to assign the one to the least possible element of gamma. And if it is dense, it is going to be just 0. And for each time, we're going to introduce a binary relation that is going to hold, essentially preserving the equivalence modulo m. What does that mean? For any two possible elements that you might have in your order Boolean group, they're going to be related if and only if their difference is m divisible. And this is the whole point, which is my language. So consider the order Boolean group with bounded regular rank, and I'm going to equip it like with a very multi-sorted structure that is very simple, but requires like to be described, let's say. So I'm going to add a sort like for the order Boolean group, and I'm going to equip it with the language of Pressburger, that sort, and I'm also going to add predicates for each of the convex subgroups. And I'm going to refer it as this one as the main sort. And I'm going to add other sorts. So for each of the possible convex groups, I'm going to add a sort for the quotient group, gamma quotient delta. This is also an order Boolean group, also of bounded regular rank. And I'm going to equip it with the Pressburger language. And I will add as well projection maps that tells me like from gamma into gamma quotient delta, essentially, which is the delta coset of each possible element in gamma. And again, well, this is somehow proof infrared, but adding constants over the home sort, and I don't want that version. So the version that should be like without adding constants over the home sort, but only adding constants here is due to Chernikov et al. In this paper of distal valued fields. But well, the idea is pretty much the same. That is, in fact, whenever you have an order Boolean group with bounded regular rank or with finite spines, then we know that gamma has quantifier elimination in this language. And what do we know about, let's say, in general, about the mode theoretic complexity of order Boolean groups? Well, there is a canonical statement that is from the 84 that says that no order Boolean group has the independence property. And the following results, somehow I divided from the other ones because the previous ones, or all the previous ones, were like sort of studying order Boolean groups for their own sake. And they were born somehow to understand the elementary extensions or like the possible completions of order Boolean groups. While the followings were more born in another sort of line of research, which was sort of finding preservation results of valued fields, which is, okay, like you have excursion, and then you want to say, okay, if you have something of X characteristic 0, if the residual field is an IP, and the order Boolean group, well, which is always an IP, if both are an IP, then the valued field is an IP, same for DP minimal, same for distal, and so on. So they appear like as somehow in valued field papers around. So first one happened to be 2015, which is Janke, Simon, and Walsberg, that characterize completely DP minimal order Boolean groups as those that do not have singular primes. And a singular prime, that means, let's say that for for each possible prime, you have that the quotients over P gamma are finite. Next one was 2017, which was, oh, no, I skipped this one. 2021 appear like for distal ones that states essentially that whenever you assume that the order N group has finite spines, then it's equivalent to have something distal to be dp minimum. And then some time ago, independently by three people like John and Dolish proved that independently for and the ones who were looking for valid field statements were Halevi and Hassan, stated that whenever you have an order N group, it is equivalent to have the order N group to be strongly dependent, to have finite degree ramp, or to have finite spines and have finitely many singular primes. And in fact, they also give like a bound for the degree rank of gamma being this. So the picture looks pretty much like this one. So you have two that are definably complete, Presburg arithmetic and order divisible abelian groups, then some powers of C or localization over C, which are those that are elementary equivalent to some subgroup, let's say, of R to the N. Extending that, you have the DP minimals. Extending that, you have those that have finite DP rank. And the class that I'm talking about today encompasses all of them in a larger case that is bounded regular rank, which is just requiring everything to have finite spines. And okay, let's get back to what I want to prove. Okay, so the goal is now you have gamma and order Abelian group with bounded regular rank. And then I'm going to argue that it is going to have weak elimination of imaginaries once you add the quotient sorts. And which are the quotient sorts? Well, I'm going to consider the main sort. I'm going to add the quotient groups of gamma quotient delta for each possible convex group, and also quotients for the groups for gamma plus n times gamma, and maps that sends, like, let's say, for each element its respective class. So this one might seem a bit unnatural, but what that is doing is just presenting in a nicer way, which is the class of each of these quotients of groups that one might have. It's just that this one is nicer to present because, well, it goes from gamma directly instead. So I don't know, do I need to define a definable type? Well, maybe. So I will introduce, because fastly. Okay, so let's say that you have P global type and P of X is a type, a big type. I'm going to say that is definable if for any possible formula, I can give you another formula that satisfies the following condition. So whenever you look at an instance of the formula phi of xp, it is going to belong to the type if and only if it satisfies the formula d of phi. And usually we call this set of derivating formulas like the scheme of the type, of the definition of the type. And well, the examples for these are essentially like any stable theory. So the canonical example, or the one that I came up very fastly, is consider the theory that has just a binary relation that says that you have infinitely many relations, each of them and each of the classes is infinite. And you might look at the type, like this is my model. You might look at the type that is in one of those classes, but is different from all of them. So this theory has elimination of quantifiers in this language. And then the defining scheme of the type is very easy, like for x different than gamma, x different than a, for any parameter a that you may pick up here is going to belong to the type. Yeah, that is going to hold like for any element. So a is going to be equal to a. And x is going to be related with a if and only if a is related with some a0. You just fix like someone in that class and that one is going to hold. And this is my defining scheme for that type. So definable types are very important, like in our setting, and I will argue why. So the criterion that I'm going to use to have the elimination of imaginaries is due to Grushovsky, but it was isolated actually by Will Johnson. So he was just reading a preprint of Grushovsky And then he realized that he was sort of proving this statement. And well, the story is sort of nice because afterwards, like the original proof of elimination of imaginaries of ACBF was quite long, like around 90 pages. And then after that, using this criteria, Will gave a proof of around 26 pages. So it can profoundly show you like how powerful is this criteria and how nice is to have density of definable types, which is not always the case. Um, well, or at least in theories, which are, well, not stable. So what does the criterion tell you? Let's say that you have a first order theory with a Helm sort K, and you have a collection of sorts. So if the following conditions all hold, then the theory has weak elimination of imaginaries down to the sorts G. So which are the two conditions that I'm going to require? One of them is to have density of definable types. So what does that mean? For any possible definable set that you give me of the field, I can give you back global definable type that is centered in X and is definable over the algebraic closure of the code of X. And the second condition is that I can code all possible definable types. So for any possible definable type that I might have in invariables, I can find a code in the sorts G. What does that mean? Well, whenever you look at P, you might look at the set of codes of the formulas that give you the defining scheme. So that will be the codes of these formulas. And then I want to have for each of those formulas a code in the sorts that I'm highlighting. Okay. So this is sort of, or thinking about this proof, it has like essentially 3 steps. In order to code definable types, when what really needs is to just characterize which are the undefinable segments. And then the construction or density of definable types, it is sort of the most technical part, but philosophically the most elementary one as well. So I will start by just describing, or like, let's say by coding the definable types, and the idea is just describing the end segments. So let's say that you have S to be an end segment. What does that mean? So I'm going to require that for any possible element. If I have an element in S and some Y in my order Boolean group, and X is smaller than Y, then I'm going to require that Y is also in S. So that looks, as you might imagine, like just an end segment. And among the class of possible end segments, I have a nicer class, which are those that are induced by divisibility cuts. So if you have a natural number and a convex group and some parameter beta, then you might look at just the set of elements, such that n times eta, let's say, plus delta is bigger or equal than beta plus delta. That is a divisibility cut, or like just strictly bigger. So for all of those, I will just refer to these ones which are nicer as divisibility and segments. And we might have like also a notion for the description of the one definable sets. So how do they look like? So a mid segment is essentially just going to be an intersection of an end segment and a divisibility initial segment. So you might take this one and then some other one. It's essentially capturing the notion of what will be like just a convex set. It might look like just like this. Then I'm going to call them basic positive congruence formula, essentially just a restriction of a congruence formula. So that I'm going to denote in this way, but just because I think it's more clear. So this notation is actually just reducing to stating that the term of this class, let's say, lies in the same coset or L gamma quotient delta divisibility coset as the projection of beta and k of gamma, where this k is just, well, k times 1 over delta, if where 1 over delta is the minimal element of this quotient if it exists. And a basic negative formula is just, well, saying that they're not related. So a finite congruence restriction is just a finite conjunction of basic congruence formulas. And an I set is essentially just a mid-segment with some finite congruence restrictions. So it's going to look like something like this. And then you might put or pick up certain points that satisfy like certain conditions. And one of the corollaries of the quantifier eliminations is in fact that whenever you look at an ordered Boolean group with bounded regular rank, any definable set is just going to be a finite union of nice sets. So it's going to look like maybe stuff like this, where you might have certain points for some of them, and some other ones here, and some other ones here. Okay. And here's like the sort of the entire point about like the divisibility in segments. So whenever you have a bounded regular rank order Boolean group, any definable in segment is actually going to be a divisibility in segment. That is sort of not very technical, but important in the sense that it allows us to precisely just code the definability in segments in these sorts, like the gammas union, like gamma quotient delta. And it seems like very important. And well, the way in which you just go is just by arguing by induction over the rank of gamma to show that you can code them here. Since it seems like many people ask me, like canonically, but why you just, like if you have a divisibility code, let's say n times x is bigger than beta, why is beta like not precisely the code of that set? And the reason is, well, you have convex groups that might ruin the stuff on the way. So that is not actually a code. So the easy example is you might just go to C squared. And in fact, if you look at this definable in segment that is just saying 2 times x is bigger than 1, 1, you might just pick up any other one in the same fiber, say 1c for c in the integers. Well, these two like instances defined the same, precisely the same in segment. So no, coding in segments is not trivial. It requires like some technical work, which is not very hard. It's just an induction, but it needs to be done. And then, okay, now we're ready to actually code definable types. And how does the argument goes? So let's say that you have an ordered Boolean group that has a bounded regular rank, and you have a definable type. And I want to show you that it can be coded in the quotient sorts. And this is like a very, very standard argument. So, okay, let's look at our definable type in n variables. So we have the quantifier elimination. And then that means that we can, or the type is completely determined by certain formulas, which are those that essentially just look at the quantifier free part. And there are three kinds of those formulas. So the first one might be just stating like an inequality between a term in C or in the variable x, which is just a C term of a coset relative to another coset in gamma, right? Or you might say as well, like the same term is bigger than this other beta plus kappa of gamma. And then the point is that whenever you look at the set of elements in gamma such that this instance, like saying having smaller than beta plus kappa gamma belongs to the type, that is actually in any case defining an segment. So by the previous part, it can always be coded in the quotient sorts. And as well, whenever you look at those that are bigger, well, that is just defining an initial segment, but those can be also coded in the quotient sorts because they're like just a complement of an segment. So those that are of second kind are just looking at a congruence formula. So whenever you look, let's say, at the set of elements such that this congruence formula belongs to your type, well, you might have two choices. Either is empty, or you might find like an element that actually satisfies or that belongs to that type, and you can pick it up. And then stating like for any other elements or parameters that might satisfy this formula is just stating that they lie in the same class as this beta. So it is just going to be interdefinable with the class of that element, mod out this quotient. And then of third kind is just precisely stating which is the coset of the beta, and the argument goes pretty much at the second part, which is just you might have something that is empty, then nothing is to be done, or you pick up someone and then the code of that set is interdefinable with the coset of that element. And then Okay, that gives us, let's say, or we're done with the second part. And then the density of definable types, as I was mentioning, is actually going to be way more elementary, but a bit more technical in nature. So what one would like to have is just generic types. In fact, so if you pick up a definable end segment, you might just look at the standard generic type that tells you, okay, you have your end segment here. And then for any possible proper end segment B, I'm not going to lie there. So I'm always looking or putting myself into the most left-hand side of this end segment. And then the relevance about the density of definable types is it is not recorded over n variables, but only over one definable sets. So if we would like, let's say, to just construct a definable type inside this end segment, everything that we will need to do is to just fix the congruences of this S, and then by the quantifier elimination, we will be done. The unique problem is that even though like fixing congruences is very easy, and once you fix them, they're definable over the coset that you have already fixed, you don't want to pick up any possible coset, but you want to pick a coset that is definable over the code of S, or over the algebraic closure of S, let's say. So that is a technical part, and is essentially pretty much like the reason for which we will need 3 lemmas to conclude. That is somehow like fixing congruences in a reasonable way. Okay, so this is pretty much like the motivation of this black box lemma that I'm not going to argue. But whenever you have an orderable n group, let's say, and an n segment, let's say that you start with some restrictions, one of them positive and the other ones that are negative, that you may have here. And then you're going to require that you look at the type that stays, okay, I'm in the generic type. I satisfy the congruences established by the positive part. And for those cosets that I need to look at in C, which are saying like I need to avoid these cosets, I might just complete by avoiding everyone in gamma. Then if it happens that for another subgroup, let's say convex subgroup H and another K, you have only infinitely many cosets which are coinitial in the intersection of these three, then they happen to be also only infinitely many cosets modulo the same group, which are just coinitial in the segment and the positive part. So you had, let's say, this big restriction that was Y, another restriction that is negative that is just C, and your X segment, and you have, let's say, my points that line all that intersection, all the yellow ones. And what this is requiring is that whenever you look at this subgroup, you have only two choices, let's say like green or blue to color those points. And then what the lemma is saying is that somehow if you happen to have the C stating like you need to avoid these other cosets, well, the same configuration will happen with infinitely many colors, also in the part where you just forget the C. So it will be also the case that for these ones, you may have also like infinitely many choices. And okay, that is like the sort of the black box lemma. And the lemma is in fact just going to argue why the following is going to work, which is the second lemma. So let's say that you have an orderable n group with bounded regular rank and you have a definable n segment. And you have a finite congruence restriction that is just going to be imposed by some positive restriction of basic formulas, and also like some negative restriction or a finite restriction of negative positive formula of negative basic formulas, say of this form. And what this is saying is essentially we know how to fix all the congruences first for those that are mentioned in C. So what we can do is construct a partial type that is going to extend the generic type, is going to lie in the congruences that we need in Y, For those that are in C that we need to avoid, it is going to be consistent, the type that I'm going to construct to avoid the elements there. And for each possible index that I might consider of those that are pure in C, I am able to actually entirely define the congruences that we need for the congruence here, delta I plus ki gamma. So I either added that I'm not related to none of them, or I was somehow like forced to add it, and then I pick it up in a reasonable way. That means I pick it up a class that was actually in the algebraic closure of the end segment and the positive part. So how do you do that? The argument is like very straightforward. So you just start approximating that type step by step by partial types gamma I, where in each of those steps, you essentially just look at the congruence that you might need in that step. So let's say that you only have one for the moment. And then what is going to be the business? Well, essentially, you might look at the generic type, let's say for this one. And then you might say, okay, can I just extend this one, saying I'm not related to anyone there? If this is consistent, then we're done. I'm just going to define this one as gamma 1. If it is not, then some work is required, let's say. And then the whole point is, well, if that doesn't happen, it's because you might have, like by compactness, some formula that was in this generic type, or a conjunction of formulas in this generic type. And some finite congruences that you might say, okay, like this one is just going to be forcing this one to be in one of these classes. So essentially you have the end segment, maybe someone or something else that you needed to take away, that was this B, and over all this convex group, you only had certain amount of congruences that you have. So if you were in your first step, actually there is not much to be done, because this statement is actually saying that you have only finitely many cosets modulo delta plus gamma that are co-initial in S. And then you might just pick up any of them that is consistent with the generic type. And then that one is going to be, of course, algebraic, because they're only over the code of S, because there are only finitely many which are co-initial in that one. But if you're in further steps, you just apply the limit that we had before. That is, in fact, you might have like already built like an approximation that was this one. And then you follow in the same way. Well, you might look at this one. And you complete, and you ask, okay, is it possible to essentially just avoid everyone in these classes? If yes, and this is consistent, then you define this one to be just the next step, and that one is fine. If not, then there is some formula that is a conjunction. And finitely many classes that you were forced to be at. And then the whole point is, how does this formula look like? Well, this formula is going to be essentially just an end segment, taking away some B. Oops. And then some restrictions, which are positive, let's say for those that were Y, and those that in previous stages you choose something that was algebraic over the code of S and Y. Or you had also, let's say, some restrictions that were negative. that I'm going to call C minus, but that means that in previous stages, you actually had added precisely all these for that congruence or this partial type that was saying that you could avoid it. And what that is saying is that, in fact, when you look at gamma I, this type is extending precisely the type that requires you that the generic type and this positive congruence, avoiding all the possible congruences here, is consistent, which is the requirement of this lemma. So by this lemma, you might just assume that, in fact, if you look at W being like this intersection S plus this part, you only have finitely many cosets that are coinitial. And then you might just complete by any of the cosets that you have there. Again, the fact of having a coset that is coinitial is expressible in first order. Since you have finitely many, anyone that you choose satisfying that property is going to be algebraic over the code of W. And the code of W by construction or all the induction is going to be algebraic or is definable over the code of S and Y. So this part of the lemma essentially tells you how to fix the entire proof. And then what you do is just complete it. This is a very large statement, but it's essentially saying the same thing for all the possible congruences that you might have that you're missing. So essentially for those that you are still completed, everything that you need to point out is that you can do this construction that we have taken so far by step by step, by just fixing an enumeration between n and n squared. And then in the stage n+1, you take care of whichever is the congruence of delta k plus L times gamma that you need to look at. That is pretty much everything that this lemma is saying. And then, well, maybe the only difference on the proof is that instead of precisely starting with the generic type, well, you start with that one where you first fix like the congruences that you needed to fix for the C. Essentially, you will have like some negative part that you need to take care at the beginning, and then you extend for the other ones as we did before. And then that is enough to actually prove density of definable types. So the statement should be whenever you have an orderable group of bounded regular rank and you have a definable set, we can find a global type that is centered at X, which is going to be definable over the algebraic closure of the code of X. So here is pretty much like super standard. You start with your definable set by the description of nice sets. You know that it is going to be a finite union of nice sets. So it's going to look like something like this. So you just go to the smallest one, which is U1, and look at one of the restrictions that might be coinitial of it, that one that you were considering. And then call maybe like one of those that you have fixed as C. If you happen to have a minimum, then the statement is obvious because that means your set has a minimum and then nothing is to be done. If not, you apply the lemma and then you pick up this partial approximation of partial types that was fixing all the congruences in the required form. You take any completion of that one. By the quantifier elimination, this type or any type is going to be completely determined by the data that you have in this partial type. And by construction, it was definable over the algebraic closure of the restriction of the n segment and the positive congruences. And of course, that is as well contained in the algebraic closure of X. So trivial. And getting back like to the main statement, if we have gamma an orderable group of bounded regular rank equivalent with finitely many spines, then what we obtain by Grushovsky's statement is that we have weak elimination of imaginaries once the quotient sorts are added. Density of definable types is all this technical work that was like sort of elementary, but not, let's say, fundamental, but and the coding of definable types, that is nicer. And the reason, or maybe what I will do is, you might wonder, can we do better actually? And no, there is no hope. The reason is whenever you have something that is a non-singular prime, that means whenever you are not in the DP minimal setting, you have for each prime P that this quotient is infinite, or like for a singular prime. And this quotient that you obtain is going to be interpretable in your group, and is an FP vector space of dimension bigger than P. And the structure induced over it is precisely the FP vector structure. So there is no chances that you could code finite sets. You cannot do better. But you can for the case that you could, which are those where that doesn't happen, which is for the DP minimal case, what you will have is, well, just add constants to name all the possible cosets that you might need, or gamma plus k times gamma in gamma. And once you fix that, well, you're fixing essentially all these quotients by constants. So there's no finite set of codes to be coded. And then, well, for those, once you consider the quotient shorts plus the constants, then you have a complete elimination of imaginary set statement. And you code finite sets essentially because over all of these sorts, you have a definable order in each of the products of the sorts. I guess I will stop there. So thank you very much for listening and for the invitation.
Well, thank you, Mariana, for the talk. Are there any questions for Mariana? Okay, in that case, I'll start a little bit. I have a couple of questions. One which is perhaps more elementary than the second. So when there was something that was confused for me in the result of Faré. So if you can go back a little bit, because you were saying that every possible convex subgroup is definable without parameters, and also there was a bound on the number of possible convex subgroups. Is that correct?
Mm-hmm.
My question is, why is not the case that kappa equals Aleph 0?
It will be that is precisely Aleph 0. So if it happens,
okay.
That's why I named it bounded regular rank. So if it happens that you have a bound,
yeah,
that bound you can show that is actually Aleph 0.
Okay, so I mean it says some kernel kappa because it can be finite, but it can also be Aleph 0. That's it. So you can use the same bound Aleph 0 all the time.
It will be like if it happens that you have a bound,
mm-hmm.
you can show that it will be bounded precisely by Aleph 0. So either you have finitely many that you need to consider,
mm-hmm.
which is essentially the polyregular case, or you have Aleph 0 of them, and that's
I see. Okay, and I mean perhaps a little bit further, although I don't know how much technical could it be. So you said at the beginning that you wanted this result to show something stronger for certain class of valid fields, correct? Eliminate. Can you state the result that you wanted to prove?
Well, there are many that I want to prove, but I can tell you the
well,
one
sorry, that you proved actually. Sorry.
So let me tell you like the sketch of my plan and why. Oh no, this is going to be repeating. Thanks. Okay. Okay, so what I know. So say that you have a valid field of X characteristic 0 and residue field algebraically closed. And value group with bounded regular rank. Okay. So, okay, like in valued fields, you have a one-to-one correspondence between the models of K and then segments. of gamma. So consider like those that are induced by all the divisibility and segments that you may have in the valued field. For S in a larger S, saying all the visibility ones. Okay. Then you might look at the stabilizer of the canonical model of each of these ones, E1 until this is just the model that you look at EI over this one. Okay. And you look at the stabilizer of that one with the upper triangular matrices, and you quotient by that one. So if you add all these sorts, then K has weak elimination of imaginaries in these stabilizer sorts. Okay. If the value group is DP minimal,
got it.
Then you have entire A. Okay. Which serves to prove as well metastability results or like residue field domination results for each of these classes. And what I'm claiming to prove soon is now consider K a valued field of equicharacteristic 0 with bounded Galois group. Then K has, if you want, well, yeah, put, in this case, like the value group is always DP minimal, okay? Because you're requiring like the to have bounded Galois group. So then K is going to have elimination of imaginaries down the stabilizer sorts plus the linear sorts, which are sort of, okay, this is what it plays the roles of like the O lattices in the ACBF case. So you might look at an O lattice M or gamma, and you look at the reduction of that one up to this one, right? And this turns to be like just the K vector spaces, where K is the residue field. Okay. So these linear sorts are precisely like just adding all these possible K vector spaces that you may have whenever like K is not an algebraically closed field. Okay, so this is what I'm claiming. That is going good, and this is known. And hopefully will be soon, like at some point, once I finish writing that, yeah.
All right, thanks. Are there any more questions for Mariana? Well, if there are no more questions, well, thank you very much again, Mariana, for the talk. And just a reminder, next week, we're going to have Isabel Müller from Imperial College, and she will be talking about Polish groups and model theory. So I hope you find it interesting. And let's see you all next week, same time, 4 p.m. Bye.
Bye.